In this video, we're going to talk about continuity and one-sided limits. Continuity is what you might think it is. It means that a function is continuous at a point or on a given open interval. A very unscientific way to think about it is if I put down my pencil and I drew along a function's curve and I don't pick up my pencil, that's a continuous function. But here we have a more formal definition. So if a function has continuity at a point, the output for whatever c constant I plug in is defined, has a real number. The limit as it approaches c from the left and the right exists, and that limit is the output when I plug in c. And so continuity on an open interval just means that the function from x equals a to x equals b, whatever those points are, the function is continuous at each point between that interval. So for example, from here all the way up to here, that's continuous. I didn't pick up my pencil. There's no breaks, jumps, gaps, holes, pointy things, anything that makes it discontinuous. Speaking of something that is discontinuous, we have discontinuity, which means that my function is not continuous at a point or over an interval. So there are three typical things that happen with discontinuity. So the function isn't defined at a certain x value. So that's like this graph here. I've got a hole, not defined, not continuous. Also, the limit does not exist. So for example, the limit is not going to exist at x equals c because I have this jump. And also the limit does exist, like it does here. The limit would be whatever that y value is, but it's not equal to the output of when I plug in c, because that would be the output, but this is where the limit exists. So those are some examples of discontinuity. Speaking about discontinuity more specifically, you can have removable and non-removable discontinuity. So looking at those examples from the last slide, we see that the first one here has a removable discontinuity. So that's like I literally take this point and I remove it. The second type is non-removable. So that was the example where the limit doesn't exist at c. So although this is called non-removable, it's also called a jump discontinuity because literally there's a jump happening here. And then the last example is a removable discontinuity just because that point exists, but it was removed from where that limit existed there. So now let's switch gears to look at examples of continuity or discontinuity. So we're going to look at four. The first is where my function f of x is 1 over x, and this may look like it's continuous because it has a piece right here and it has a piece right here, but obviously this function doesn't exist when x equals 0. So that's going to be a non-removable discontinuity at x equals 0. The second one is this function here. We have a rational function because I have a variable in the denominator. So it's not defined, our domain is not defined at x equals 1. So there's going to be a hole there. That's going to be a removable discontinuity at x equals 1. Two more examples here. Let's say I have this piecewise function defined as h of x, and this is going to be continuous because I could literally take my pencil and continue that there. There's no jumps, breaks, gaps, etc. And then the second one is just sine of x, and sine of x, if you didn't know already, is continuous for all real numbers on its domain. So that is a really classic continuous function. Next, let's talk about one-sided limits. So I can have a limit that approaches a point, some c, from the right, which would be indicated by a plus in the exponent spot next to that constant, or from the left, which would be a negative in the exponent spot next to that constant. So a point on a function can have a right-hand or a left-hand limit, and they can honestly be different values. You just have to specify that the right-hand limit is this and the left-hand limit is this. But when they are the same value, so for example here they're both some value, whatever L is, that's going to mean that the existence of just the limit as x approaches just some c from the right and the left mean that that limit exists at that point. And just a quick example of that. Let's say I have this function here, this radical function, and let's take the limit of that as x approaches -2 from the right. So I'm going to come in on this function and approach -2. So the output there is 0, so that means the right-handed limit of that function is going to be 0. And here's an example of a right-hand and a left-hand limit of a function that just doesn't match. So this is something that we call a step function. This is a specific step function called the greatest integer function, denoted as these two brackets here. And so literally it looks like a step, hence why it's called a step function. So it exists where it has a closed circle and then this straight line here and then an open circle where it picks back up on the next integer on the output. So let's say I want to take the limit of the greatest integer function as it approaches 0 from the left and the right. So if I'm going to take the left-handed limit, I'm going to come in this way from the left, and I'm going to start here at -1. I'm going to come in and I'm going to see that, all right, that limit on the left-hand side is -1. But if I approach from the right-hand side, I'll start right here and I'll end up at 0. So those two things do not line up, so I can't say that the limit as x approaches just 0 exists, but the right hand and the left hand exist separate from one another. So we're going to take this and talk about continuity on a closed interval. And that basically says that from any closed interval where x equals a to x equals b, I have a continuous function. So whatever the outputs are, this example here shows that if I take the limit of a coming in from the right and I take the limit of b coming in from the left, that thing is going to exist and be continuous from that interval. A really great example of that is this function here. I have the square root of 1 minus x squared, and it's continuous from -1 to 1 inclusive because I can find the limit going this way and going that way as I approach -1 and 1 from opposite sides. Plus it's continuous. You can see it's continuous. There's no jumps, gaps, holes, etc. And here we have some basic properties of continuity. So these rules are predicated on the fact that b is a real number and the functions f and g are continuous at some point c. So then anything that I do to that, so if I multiply that function by a scalar, if I multiply the two functions together, if I add or subtract them, or if I divide one by the other, provided that the denominator doesn't equal 0, that means that if I perform those operations on those functions in any of these ways, and as long as those original ones are continuous, the resulting functions will also be continuous. And also, continuity of a composite function, if g is continuous at some point and f is continuous at whatever the output of plugging in c into g is, then that means that the composition of f of g of x is also going to be continuous. So now let's look at a couple examples where we take a function and test for continuity. So let's first take a function we're probably familiar with, and that is tan of x. So something to know about the graph of tangent, it's that it's undefined, add pi over 2 and every pi multiple of that afterwards. So we express it like this. So that means that in those intervals, so for example, from -pi over 2 to pi over 2, that function exists. It's continuous. So you just list out where those things are continuous like this. So this is an interval, that's an interval, that's an interval, etc. So you can have continuity that repeats on a certain interval, and that's how you write it. So here's another example. So this is a piecewise function, and I'm going to have sine of 1 over x here as my main function. So we know that 1 over x as a function is continuous except wherever x is 0, because there's a break there, and the sine function is all real numbers across its domain. So if I put those two ideas together for sine of 1 over x, that means that that thing is going to be continuous except for where x is 0. So that has a continuity that just doesn't exist at one point. So I would write it like this. So like its domain goes from -infinity to 0, stops there, picks back up, and goes to infinity. Let's look at one more example to test for continuity, and it's going to look a lot like the last example, except I'm going to throw in an x right here. So I'm going to apply the squeeze theorem that just says that this function in black here, which is x times sine of 1 over x, is squeezed between the absolute value of x and the negative absolute value of x, so these two lines here. And so I know that the limit of this function as it approaches 0 is going to end up at 0 because there's not a discontinuity there. So that means that this function is continuous for all real numbers of x, so that's negative infinity to positive infinity. And last but not least, let's talk about the intermediate value theorem. So big words usually mean a theorem that's pretty easy to understand. All that means is that on a closed interval from a to b, I have some outputs, f of a and f of b. And as long as these two things are not the same value, that means that I'm going to have some intermediate value output for some c. So that means between a and b, that means that whatever this output is for a, whatever the output is for b, there's going to be some number in between that exists as long as that function is continuous along that interval. A really practical application of this is, let's say on my 13th birthday I was 5'2", and then on my 16th birthday I was 5'7". It's not like all of a sudden I went from 5'3" to 5'7". Gradually over time I was 5'4" and 5'5" and 5'6". So I must have hit the intermediate values between my 13th and 16th birthday as far as my height went. A really good use of the intermediate value theorem is proving that a function has a 0 on a certain interval. So let's take this polynomial here, for example, our f of x, it's a cubic, and let's prove that it has a 0 on the interval between x equals 0 and x equals 1 inclusive. Now the way that I do that is I plug in 0 for x and 1 for x, and I realize that my output at 0 is going to be -1, so that's going to be plotted at this point 0, -1, and then when I plug in 1 for x, I get an output of 2, so that's the point 1, 2. So no matter what that function looks like between x equals 0 and x equals 1, I know I've got to cross the x-axis to find my 0 at some point, so there's at least one 0 between x equals 0 and x equals 1. In fact, here's a better looking visual of that graph. So we actually do hit the 0 at some point between x equals 0 and x equals 1. Now that's going to do it for this video. Thanks for watching.